Okay, so here's a couple more scenarios that we're going to look at using Newton's second law. Okay, these ones are a little bit more complex, okay, because there are systems with two objects in them. And so I'm going to start with this one right here. Okay, and so what we're going to do is we're going to draw a free body diagram for each. And then for situations like this where we have a cable or like a cord, we actually take the coordinate plane and we like kind of bend it. Okay, so the direction of the x-axis is going to bend like this. And the same thing here, the direction for this one of the x-axis is going to bend around like this. Okay, and so what we're going to do is we'll start with this one. So for this block right here, we have the weight downward, and then upward we have tension pulling. Okay, and then for this one right here, we have in the direction of motion, we have tension. We're going to assume it's frictionless right now. So we have tension, you have the weight, and the normal force. Okay, now I'm going to show that there's two kind of methods we can use here. I'm going to show one of them on this one and the second one on this one. Okay, so what we're going to do is we're going to write for each block, we're going to write an equation for the net force acting in the plane of acceleration. So remember we have it kind of bent downward, and so it's going to, for any forces acting in this direction here, we're going to write an equation for those. Up and down here, they're balanced, so we can say that's equal to 0, and we can ignore that here. So for this object right here, little m, so the sum of the forces acting on little m is going to be equal to little m times a, and the only force acting there, we'll say this way is positive, so we have positive t. Okay, for the second object, we'll do the sum of the forces acting in that same plane for the second object. So for this one, we're going to say, alright, big M times A. Okay, and for this one, in the positive direction, so we're saying this way is positive, so pulling this way is the weight, mg, and then pulling back up, we have minus t. So we have two equations here. We want to solve this for acceleration, and so what we're going to do is we're going to add these equations together, do elimination, as you'll see we can eliminate t. Okay, so we add these together, t and minus t will add to be 0, so we have little m times a plus big M times a equal to mg. We can factor out a from here, so a times little m plus big M is equal to big M times g, and then we'll divide that over, and so we get, in this case, the acceleration equal to capital M over little m plus big M times g. And so that is the acceleration of this system. Now what you can see is that the acceleration is a ratio between the total mass and the mass / weight of this falling object. Okay, so this is the only force causing this system to accelerate, and this is the total mass here of the system. Okay, and so if this object here would, if it was in free fall, it would just fall at the rate of g. Now since it's also causing this object here to accelerate, it's got the combined mass down here. Okay? Alright, moving over to this question right here. We're going to set up our plane like this. We're going to curve it. And for this one, we're going to use a different approach in which we find the net force of the whole system in that plane. So all the external forces acting on the system. So in this case, we're actually going to ignore tension. Okay, going back to this one, if you wanted to solve for tension, you could take this value here, whatever you get here, and plug it into A there and solve for T. Okay, so in this scenario here, we can say, okay, on this system, on big M, or on little m, we have mg this way and T this way. And the other one we have big mg this way and T this way. So if we're going to write a net force equation for the whole system in this plane, we're going to have to add the combined masses, m plus m, times their acceleration. So we'll be equal to, we'll say in this positive direction we have this force mg. Okay, you can say we have minus t, then we have plus t. So these are going to go to be 0, so we can just kind of ignore them. And then we have negative mg right there for little m. And then we can say, okay, we can divide that over, we can factor out g, and so in this case, the acceleration of the system is equal to m, capital M minus little m, over m plus m times g. Okay, and you can see that this system has less acceleration than this system because these masses are fighting each other, right? Their weights are fighting each other a little bit, and so the net force on this system in this case is a little bit greater than it is in this case. Okay? I have another scenario with an elevator. You have a person standing on a scale in this elevator. They have a mass of 80 kilograms. The elevator has a mass of 1,000 kilograms. And what I want to do is I want to find their weight so not their weight. So let's think about it like this. When you weigh yourself on a scale, the scale is measuring basically like the normal force, or how hard the scale has to push back up to keep you balanced. Okay, and so what we're going to determine is the reading of that scale for when the acceleration of the system is 0, for when the acceleration is, let's say, positive 2, and for when the acceleration is equal to negative 2. And so what we're going to do is we'll do a net force equation for the scale, or for the person rather, and so we'll say they have a downward weight, mg, there's an upward normal force acting on them, and so we can do a net force equation in this vertical direction. And so some of the forces acting up and down on them, they are not necessarily in equilibrium, so we'll say this is m times a, and then we have this, we'll say up is positive. Okay, so we have an upward normal force, Fn, minus downward weight. Okay, and so what we want to do is solve for what this normal force is. So Fn is equal to m times a plus m times g. And so Fn equals m times a plus g. Okay, and so now what we can do is we can plug in these values to kind of think about what would happen. Okay, so if acceleration is equal to 0, then we put this in for 0, in which case the normal force would be equal to m times 0 plus g. So if the elevator moves at a constant speed, meaning no acceleration, then what we see is the normal force is equal to the weight. But let's say we have upward acceleration of 2 meters per second squared, then the normal force is going to be equal to m times 2 plus g. Okay, or basically like mg plus 2m, so like a little bit more than the weight. Okay, or in the case that it is accelerating downward, normal force would be equal to m plus negative 2 plus m times negative 2 plus g, or the normal force equal to mg minus 2m. So again, in this case, we have slightly smaller normal force. So what this means is when you're in an elevator and it has upward acceleration, then you momentarily feel heavier. And when you're in an elevator and you have downward acceleration, you momentarily feel lighter. Okay? There's another question we could ask. Well, what if your acceleration is downward at, so negative g, so downward at the rate of gravity? So basically, like if this cable has been cut and you're just falling downward, what is your acceleration then? Or what is your weight then, or the normal force? And so what we're going to do is say Fn equals m, and in this case a is going to be negative g. Okay, which means this will be equal to 0, and then the normal force you experience is equal to 0. Okay, and so this is why when something is falling, or like if you are falling, you feel weightless. And this is why the astronauts in space are weightless, because they're falling around the Earth. Since nothing is pushing up on them, they feel no weight. just like with you, if you're falling, nothing's pushing up on you, so you feel no weight. In order to feel the weight, you have to feel the normal force pushing up on you. Okay? We could also talk about the tension experienced by this cable here from the elevator, and then what you would do is, instead of this being the normal force pushing up, it'd be the tension pulling up on the elevator.